This is the second segment of the plate tectonic chapter in historical geology. We stopped at the rift basins, and now we're going to continue with the deposits in the rift basin. If you think about what kind of situation is the rift basin, we have mountains. If it's a graben fall, then you're going to have mountains on both sides and like one basin in the middle. In this case, it's actually a so-called half graben. When you have a half graben, then you only have one normal fault and the other side is kind of flattens out. But a lot of the times, I already told you that we have the typical graben fault. In that case, you got mountains on both sides and the sediment is coming into the basin from the mountains. So in the middle of the basin, usually you have like, if it's in dry area, obviously, you got a dried up bed. During the springtime when you have a lot of rain, you're gonna have water in here, but during the summer it all dries up. So you're gonna have, because these sides are really steep, you have a lot of alluvial fan, very typical, which has very, very immature, unsorted breccias, conglomerates, and you have some braided stream probably. You might have some typical cross-bodied sand dunes if it's arid. And you also will have salt, like gypsum anhydride salt, typical from when the lake dries up, all those deposits are very characteristic. So this is what you got in a typical rift basin. Mostly unsorted breccias, conglomerate, immature, but then also you could have typical sand dunes around here. And it's very, very characteristic stuff in the Death Valley. Very similar situation, actually. So these are the sediments in the rift basins. And now the second part of the continental breakup is the oceanic drift. This is when the rift basins become wide enough for the ocean, the salt water to come in. And actually it gets wider and wider. So the sides are becoming actually so-called passive margins. And these larger basins are going to be filled up with typical continental sediments. So on this side, this is typical rift basin at the beginning, which is getting wider. Now the ocean can come in, so you're going to have seawater. And these areas are the ones which used to be a very active plate boundary, as long as it was a rift basin. But now that we have this wide ocean, such as the Atlantic, with the mid-oceanic ridge, where you still have the volcanoes forming, the magma is coming up, these areas are now becoming very inactive. We call them passive margin, passive margin. When you have the typical passive margin and well-developed mid-oceanic ridge, we call it oceanic drift, oceanic drift. So right here it's a typical situation. We are on the Atlantic Ocean, and northeastern North America is on the side of the Atlantic Ocean. It's inactive plate tectonically, so we call it passive margin. If you drill down or you look at a seismic profile, you can clearly see the initial rifting with the typical normal faults, graben faults, and so on. But then it filled up with sediment, and now we have the mid-oceanic ridge activity somewhere far away, and here we have typical passive margin. Usually on the passive margins, you will have mature sediment if it's a big continent, and the sediment is being deposited on the top of the original normal faulting area. So this slide just shows this picture, basically just showing you the Atlantic Oceans. To the side of it is typical passive margin, that's Europe, and Africa is Western Africa, and then Eastern Europe right here, Eastern America, sorry, it's not Eastern Europe, Eastern America, like Virginia, North Carolina, go up, New York, all that is typical passive margin. Some ancient examples for rifting. It's right here in the eastern United States. That's where the Atlantic Ocean started to open up, and we have all these rift basins here. Of course, they are filled up with sediment completely, and now you wouldn't be able to pinpoint it. Of course, if you know the sediments of a rift basin, you could possibly. But we do have all these covered rift basins, uh, seismic profiles, boreholes. We can prove all the mafic igneous rocks around Washington, D.C. We have a whole lot of it. The famous Palisade Seal in New York. So it's all over the eastern U.S. These ancient rift basins are all around us. Now this slide shows you all the ages of the oceanic crust, and the blue being very old, and the young is the red, basically the present days. And if you look at the Atlantic Ocean, you can clearly see where it started to break up. It was right here at the eastern US. I have to change the color of this pen. Let's say I'm gonna change it to pink. I think it works. Does it work? Yes, pink. So this is where it's the oldest. That's where it started to break up. But the pink, the red is everywhere in the exact middle. So it's a very typical, absolutely symmetrical on both sides. So there is no any kind of convergence going on in the Atlantic Ocean. Don't forget, it's a typical widening ocean. There is no convergence. The mid-oceanic ridge everywhere is in the middle. Okay, the oldest part of the Atlantic Ocean is right next to the eastern US and western Africa. That is where it started to open up. You can see that the South America and South Africa started to break apart much later than North America, Eastern North America and Western Northern Africa. That started much earlier than down here. It's kind of interesting. If you check the age of the oceanic crust, you basically can tell this kind of things. It's very, very interesting. Okay, so now the next thing we have to talk about, if the Atlantic Ocean opened up and the volume of the Earth is the same, then something has to happen on the other side. And if you look at the Pacific Ocean, it's very strange. Look, Atlantic Ocean is being so symmetrical. On the other hand, if you look at the Pacific Ocean, the mid-oceanic ridge is definitely not in the middle. And if you look at the two sides, you have some blues here, but there is no blue on the other side. So what happened with the other half of the Pacific Ocean? Obvious, it went underneath of North America and South America. But it's still active. So basically the mid-oceanic ridge here is moving underneath of California. So let's go through the different convergent plate boundaries. We have to talk about when an oceanic lithosphere plate meets another oceanic. Remember, as on one side it's opening up, on the other side it has to shorten, because that's the only way you can keep the same volume. So when you have two oceanic plates being pushed together, you know, one will have to go down. When you have a continent and ocean, the oceanic will go down. Continent can never, remember, because it's lighter than the oceanic plate. And when you have two continents, what happens? Can any of them go down? No. So what will happen? They'll have to actually, the only way they can go is up, because they're lighter than the mantle, so they cannot be pushed back down. So the only way they can be pushed is to up. So this is when big mountains are forming. So Oceanic-Oceanic, Oceanic-Continental, Continent-Continental. And remember, I always am talking about lithosphere plates. So it should be Oceanic-Oceanic plate boundary. But I mean, it says it right there, so we're good to go. So let's start with the Oceanic-Oceanic. Before I jump in, I kind of already showed you that along the Pacific Ocean, you know, the mid-oceanic ridge is going like that. And everywhere along the mid-ocean, around the Pacific Ocean, we have convergent plate boundaries. And so therefore, the best example is going to happen along the Pacific Ocean. So let's start it. This here is the Oceanic-Oceanic plate boundary. When you have Oceanic-Oceanic plate boundary, one oceanic plate will go under the other one. And remember, this is the zone we call subduction. It's SUBDUC. Subduction. So that's the word subduction. That is when the plate is going down. And this is oceanic plate. It's important that you will say oceanic plate. And here is the other oceanic plate. And right where this is all underwater, as you remember, we learned it in physical geology. And as it goes under, magma starts forming when the temperature gets to the 1000 or so degree. Melt is forming, and because it's less dense, it's gonna go up and actually will produce volcanoes, and that's what we call volcanic arc or island arc. Either way, they are synonyms. And you will have the deepest part of the ocean, the trench, right here. Now, right here in front of the volcano is what we call forearc basin. It's important that you will know these words. Behind the volcano, we have back arc basin right here. That's the back arc. So forearc, back arc basin. These are important to know because they have very characteristic sediments. So if you go back in time and you see typical forearc or back arc basin sediment, you know what kind of plate tectonic setting we have and what kind of geologic resources you can find in these settings. So it's important that you're able to tell long time ago what kind of plate tectonic setting we had from just the sediments, because we don't have volcanoes anymore. You know, it's like gone. All you have is the rocks and the sediments. The best example for oceanic-oceanic plate boundary is Japan. And that's just a block diagram showing the exact same situation. This is oceanic-oceanic, and I told you that the best example for this is Japan. And here is the satellite picture for this typical thing too. When you have oceanic-oceanic, everything happens underwater. And remember, you have the oceanic plate going under another oceanic plate. And the magma is forming. So the magma is always forming on the plate, which is not going down, because it has to go down for the magma, for the rocks to go into warmer environment and the magma forming. So you will always have the islands on the slab which is not going down. So we know for a fact that the Pacific plate is going down here, and this one doesn't. So it's kind of cool because you are able to tell them. And the trench is right here. So that's right here is the trench. So this is typical oceanic plate boundary. And this slide, these pictures showing a very interesting thing. The way we know the angle of the subduction zone is that you map the depth of the earthquakes against the epicenter. And that actually is really going to show you the angle of the subduction zone. And you can see it right here. Right here. So the red ones are the deep focus earthquakes. The blue ones are the shallow. And so on. So you can actually map it. And if we will do it in lab, you might have already done it because I like to have that done. So you probably know what I'm talking about. If not, I hope you understand from just what I said. Remember the depth of the earthquake versus that epicenter on the surface is going to give you the angle of the subduction relative to the horizontal plane. So it's kind of really cool. The next kind is the Oceanic-Continental plate boundary. Remember, oceanic plate, continental plate. And the only thing which can actually subduct is the oceanic plate. Remember, the continental plate is light, so it cannot go down. So the subduction always happens and the oceanic plate goes down, subduction. And I just put SUB, subduction. And again, the magma is forming. And it will produce volcanoes, but the volcanoes always going to be on the continental plate. Always on the continental plate. So it's easy to draw. And the different basins you will have to know is, again, the forearc, which is in front of the volcano toward the ocean, right next to the trench. And then on the continent, in front of the volcano, you will have the so-called foreland basin. So you remember, this is foreland basin. And that's the continental plate, foreland basin. And I couldn't find anything better than this. Here is the typical foreland basin, and you got the trench and the forearc basin. So it's the western U.S., as you can see, typical foreland sediment. One of the best examples for Oceanic-Continental plate boundary is the Andes. So Andes is the best example for it. Here is the oceanic plate going down. Here is the trench, and you got the volcanoes on land. And Northern America, really, actually Oregon and Washington, is typical Oceanic-Continental plate boundary. This is where the Juan de Fuca plate is going underneath of Oregon and Washington. So we have these typical mountains, Mount St. Helens, Mount Rainier, Mount Hood, the Three Sisters. These are all Mount Washington. These are typical Oceanic-Continental plate boundary mountains. So this was the Oceanic-Continental plate boundary. The third kind of plate boundary is when two continental plates meet. The way it happens is that usually there is an oceanic plate boundary, so it's first going to be Oceanic-Oceanic, then it's going to be continued by Oceanic-Continental, like right here, and when all the oceanic plate is gone, it went under, then the two continents meet right here. You still will have the remnants of the oceanic plate, which is going down before, and now the two mountains is going up, making really, really high mountains, such as the Himalaya. The Himalaya actually is one of the best examples for continental plate boundary. We also call it collision. Or we say that India is colliding into Asia, and the product of that collision is the Himalaya mountain. And this is an amazing picture of this. India is going up north and colliding with Asia, producing the Himalayas right here. Okay, so now we're going to talk about the sedimentary basins along the convergent plate boundaries. We just mentioned the forearc basin, and if you think of the forearc basin, it is right in front of the volcano, and then you have the trench right there, which is very, very deep ocean. So the sediment is typically coming from the volcanic arcs, and you're gonna have very mature, very unsorted sediment, which is coming from the volcano exactly. So it's going to be very mature, full with rock fragments from the volcano. On the other hand, the back arc basin is going to be very similar, basically, because you're going to have the sediment coming from the volcano again. So when you have the Oceanic-Continental plate boundary, then you have the forearc, which is very similar to the other forearc. But in the foreland basin, you have sediment from the volcanic arcs. So those sediments will be mostly continental sediment, and some of it is coming from the volcanic arc, which means it's going to be pretty immature and unsorted sediment from the mountains. The last type of plate boundary is the transform plate boundary, and we have gone through in physical geology. That's when you have the mid-oceanic ridge, and the mid-oceanic ridge actually is not one plate, but it's broken up by these transform plate boundaries when the plates are sliding next to each other. So this is the mid-oceanic ridge, transform plate boundary. So that's the typical nobody really knows why that happens, but it does. And this picture here shows it clear. So that's a transform plate boundary, that's transform, and this is the mid-oceanic ridge right there. And the best known example for transform plate boundary is the San Andreas fault. And remember, the San Andreas is right running through. It says the mid-oceanic ridge goes under. One of the transform plate boundary went up to North America. So this is the San Andreas fault, and San Francisco actually is on the North American plate moving this way, and Los Angeles right here is on the Pacific plate moving this way. So you can clearly see if you're standing on the Pacific plate and you look at the North American, that it is what kind of plate boundary? I mean, what kind of transform fault, I should say. Remember, we had the left and right retro. So if you're standing on the Pacific plate looking at the North American plate, it goes to the right. So it's a typical right lateral strike slip fault. This just shows you when you have a strike slip fault and there is an earthquake, then if you had fence, it might just move away from each other horizontally, which is crazy, kind of. And that's a close-up of the situation, actually. This is when in Washington and Oregon, the Juan de Fuca is going under. It's a typical Oceanic-Continental, and then here is the San Andreas fault. And now these are the hotspots. Remember, in physical geology, we learned about the hotspots. These are hot mantle plumes which are breaching the surface in the middle of a tectonic plate, such as the Pacific plate. And because it's hot, you know, it melts, so it goes up because it's less dense, and we'll just make the volcano. And in this case, what happens, you have the hotspot right here, and the oceanic plate is moving over the hotspot. So you're going to end up with a chain of volcanoes, but only one is active and the other ones are not. Those are inactive. So it's the typical so-called hotspot volcano. I'm going to stop right here, and we'll continue it with the third segment.